Hello everyone, we are Team UGFS2 and today we'll be presenting our project MASCoD MLIRBench, which is Multi-Agent Semantic Code Divergence Benchmark for Compiler Optimization. Our team members are Pranava, Meghashyam, Kaining, and Farhan. The main idea behind this project is to evaluate whether large language models truly understand compiler semantics at the MLIR intermediate representation level instead of just relying on syntax or pattern matching. So, rather than asking, can the model generate code, we instead ask, can the model reason about compiler behavior, semantic equivalence, and execution divergence? So starting off with the home page, this gives an overview of the entire MASCoD MLIRBench framework. At the center of the system are four major agents: the mutation agent, the execution sandbox agent, the LLM reasoning agent, and the judge agent. These agents work together as a coordinated semantic evaluation pipeline. The mutation agent generates controlled MLIR mutations across different semantic levels. The execution sandbox agent then compiles and executes both the original and the mutated programs using ERI to generate execution grounded truth. Then the LLM reasoning agent evaluates whether models can correctly reason about the semantic relationship between the two programs without seeing execution outputs. And finally, the judge agent compares the predictions against the actual execution evidence and scores the reasoning quality. The overall goal here is to move beyond source level benchmarking and evaluate reasoning directly inside compiler IR representations. Now, moving on to the architecture flow. This section goes deeper into the architecture and research motivation behind the project. One thing we realized is that most current benchmarks evaluate high level programming languages, but compiler infrastructures actually operate at the intermediate representation level where semantics become much more sensitive. So, MASCoD MLIRBench focuses specifically on MLIR because it exposes tensor semantics, SSA dependencies, affine indexing maps, iterator behavior, and compiler legality constraints. The benchmark currently supports Torch and Linolch dialects, and every mutation flows through a fully execution grounded pipeline. We also designed the system such that every evaluation remains auditable. So, for every benchmark sample, we preserve mutation metadata, dependency graphs, execution traces, semantic labels, and reasoning outputs. This allows the framework to function more like a research infrastructure instead of just being a static dataset. Moving on to the leaderboard section, this is where we present the benchmark results across 5 open source and 3 closed source models. We evaluated Claude Sonnet 4.5, GPT OSS 120 billion, Kimi K2.6, GPT 4.1 mini, Qwen, GLM 5.1, and Llama 4. One of the biggest findings from our experiments was that even the strongest models still struggle with exact compiler level reasoning. A lot of the models can often correctly guess whether two programs are equivalent or divergent, but when it comes to predicting the actual execution behavior causing that divergence, the performance drops significantly. The hardest cases were the structural mutations, compiler legality violations, and failure inducing transformations. And that's important because it shows the compiler semantic reasoning is still a major open challenge for modern AI systems. Next is the dataset section. MASCoD MLIRBench includes a curated corpus of MLIR semantic divergence samples. The dataset stores original MLIR programs, mutated programs, execution traces, runtime statistics, semantic labels, dependency metadata, and compiler diagnostics. We currently support Torch and Linolch dialects with multiple mutation categories across different semantic levels. The dataset is designed not only for benchmarking but also for downstream tasks such as semantic reasoning fine-tuning, compiler failure correction, and execution-aware AI research. So overall, the idea is to provide a fully structured semantic audit trail for every evaluation sample. The About page explains more about the systems and infrastructure side of the project. MASCoD treats semantic divergence as a systems problem rather than only an NLP problem. The framework combines MLIR tooling, compiler validation, execution sandbox, HPC infrastructure, and semantic evaluation pipelines together into one integrated system. We also use deterministic execution environments and compiler validation workflows to ensure reproducibility across evaluations. And since every stage is tracked and logged, the framework supports scalable and auditable semantic benchmarking experiments. Finally, this is the live benchmark demo. Here, a user can directly interact with the MASCoD pipeline by selecting a dialect, choosing a mutation level, entering the MLIR code, and launching a semantic divergence benchmark run. Here I have my MLIR code from Linolj dialect at level 2. As you can see, the explanation gets modified based on the level. So level 2 is intermediate, where we have dependency aware shape, operand, and op order perturbations. Once submitted, the system takes approximately a minute to a minute and a half to generate controlled mutations, validates compiler legality, executes both programs in the sandbox, and evaluates semantic reasoning by producing execution grounded results. The interface also displays validation status, dependency graphs, mutation traces, and the final mutated MLIR output. So, as you can see, once the benchmark completely executes, you can see the mutation level, dialect, the verification status, and the validation from Nova cluster, and the dependency graph, and the input and the mutated MLIR code. So, to conclude, MASCoD MLIRBench introduces a new direction for evaluating AI systems directly at the compiler IR level. Our experiments show that while current models retain some core semantic understanding, they still struggle with exact execution reasoning, compiler legality understanding, and deeper structural semantic analysis. We hope this benchmark helps support future research in compiler-aware AI systems, MLIR specialized reasoning models, and execution-grounded semantic evaluation. Thank you.